Hello everyone, we will use the same translational mechanical system to show the state space representation. For the state space representation, first of all we will write the equations, then in the next video we will convert them into the matrix form. But for now, we should start with the state variables determination. So state variables means smallest set of variables to describe the system. And we should focus on the storing elements inside the system. So because of this, and as a first step, we should decide our state variables for the system. What are they? For such a system, it should be the displacement and the velocity to describe the storing elements of dashpot and the spring in terms of the equations. So these are related with each other, displacement and velocity. So if we have a relation to show between them, we have to write at the step. So as we know, we can write x dot, the first derivative of the displacement, will be equal to v, the velocity. So after that, we should write an expression, a mathematical description equation for the system. So we did this in the previous video by using the D'Alembert law. We obtained the mathematical equation for such a system. What we did, we drew the free body diagram for the mass, and we use arrows to show all the forces on the system. So the dashpot effect, and also we have mv dot for the inertial force. And then, according to a similar application of the Newton's second law, by applying the D'Alembert law, we add all the arrows according to their directions, and we accept the Fa as positive because of the applied force will start the process. So mv dot plus vv plus kx, it is equal to Fat. This is our mathematical equation for this system. According to our first step, the determination of state variables, we can write our state variable equations. What does it mean? If these are our state variables, that means we have to write an equation for each of them. In the equation, the left side must include the first derivative of this state variables. So we will find a differential equations for the state variables. So that means if our state variables are the displacement and the velocity, so we have to write two expressions to obtain their first derivatives. So the first one, it is written in the first part. It's our additional expression to show the relation between x and v. For the second one, we can use our mathematical equation and we can take v dot. That means 1 over m, and inside the parentheses we have minus kx minus bv and Fa. Okay, this is the state variable equations for the system. In addition to that, in this representation for the further analysis part, we should decide or we should determine our outputs, and we should write our output equations. And before the output equation part, we should say for the state variable equations, on the left side, yes, we have the first derivative of the state variables, but on the right side, we have to see only state variables, x, v, and input. Okay? Nothing else. As the variables on the right side of these equations, we have to see state variables and or input. If we have another parameter, we need to change it. We need to rewrite by using an equation like this to show the relation between the parameters. After that, let's write the outputs. Outputs can be anything related to the system. According to our point we want to focus on, we want to analyze, we can select any parameter for the system. For example, the spring force can be an output. The velocity can be an output. The acceleration of mass can be an output. Displacement, dashpot force, anything related to system can be an output to examine the system operation. So for Fk, we wrote the spring force expression previously. It is K times X, spring constant times the displacement. The important point, again, we should check the right side of this output equation. On the left side, we have output parameters, and on the right side, we must see only the state variables and or FA, that means the input of the system. So X is our state variable, so there is no problem. We can use as Fk, spring force, this equation. What about velocity? Velocity is equal to velocity. Velocity is our state variable, so I can use this parameter. No problem. And the last one, AM, the acceleration of mass. We know acceleration means the first derivative of the velocity, so I can use my second state equation for that part. So it is also equal to v dot, the first derivative of the velocity. And for that part, I can write 1 over m minus kx minus bv and fa. Because I know the right side includes only the state variables and the input. So I can use as outputs these equations. Thank you for watching.